Okay, we return to our discussion of quantum theory, non-locality, and DeWitt's chapter 28. When I just left off, I was talking about how the EPR experiment is a thought experiment. It's not one you can carry out and learn anything from, because you can't carry out a measurement to determine what would be happening if you weren't measuring, and that's really what the EPR experiment is about. John Bell, an Irish physicist in the mid 1960s, basically modified the EPR experiment into something that you could actually do and learn from. So, a little more rigorously than EPR had done, he shows the incompatibility of quantum mechanics and locality. And so he gives you, even though, like Einstein's special relativity paper, it's really a mathematical proof, it's also a recipe for designing an experiment. The technology at the time did not permit the experiment to be designed, but Bell's theorem, Bell's inequality, whatever you want to call it, is a way of showing that you could get an experiment in principle to determine whether locality or the standard interpretation of quantum theory was correct. So we have an experimental setup like the EPR experiment. We're talking about twinned photons. We're using polarization. It doesn't have to be polarization. Lots of quantum phenomena are embodied by twinned particles. What is crucial mathematically is that you need 3 settings on the detector, not just 2. This is going to give us the mathematical expressive space to see that locality and quantum theory make different predictions. Fortunately, there really are such settings. So DeWitt has it in terms of like a soda machine. I'm from the South, we call it a Coke machine with just left, right, and middle settings. That's fine. That gets you the basic mathematical structure. If you want to think of it that way, knock yourself out. If you want a slightly more realistic sense of how this worked, you can think of the settings as choosing the axis along which a particle's spin is measured. That's not going to give you the full story, but DeWitt's example is a little fanciful, but it really gets the structure pretty much exactly right. Now, when you've got 3 settings, if you set the detectors differently from one another, you won't always get the same result for each detector, right? Even though you've got twinned particles, the different settings in the detector will cause you not to get the same result. Remember, with twinned particles, if your detectors are identically configured, the random result will be the same for both particles, right? It's 50% chance of an up detection, 50% chance of a down detection, 100% chance that if the particle you shoot off to the right is detected up, the one that you shot off to the left will be detected up. That is provided that your detectors are identically configured. But you could set your detectors differently from one another on purpose so as to get divergent results. What Bell shows you is that given locality, the detectors can account for at most a 50% divergence in outputs. DeWitt's discussion in chapter 28 is useful here. Messing with the settings on the first detector can generate at most a 25% difference, but can't affect the other detector, right? Because nothing can travel faster than light, and not even light could get from detector A to detector B in the amount of time involved. So you put those 2 together, assuming locality, right? You can account for at most a 50% divergence in the results. Quantum mechanics, though, predicts a more than 50% divergence. So Bell shows in much more mathematical detail than EPR had that quantum mechanics makes testable, in principle, predictions that are incompatible with locality. Now, I like DeWitt's discussion very well. I don't think he brings out quite as straightforwardly as he might have that this is just a mathematical result. Again, you can compare this to Einstein's paper on special relativity, which doesn't require any math higher than algebra and is really just a consistency proof. What's really going on here is Bell takes the notions of randomness, right? It's random whether you're going to get an up or down polarization. That tells you something about long-term frequencies, right? And the number of possible detector outcomes. There are only so many possibilities, and given that the results are random and you can only generate so many different possibilities of agreement or disagreement, basically what he's doing is showing that locality can only give you a 50% divergence. If the details of that tend to escape you, I wouldn't worry about it too much. I'm just trying to show you that Bell's result is just math. He looks at the notion of randomness and how many possible outcomes there are, and then basically you just count them up. And given locality, there can only be a certain amount of divergence. All right, I'm going to try to keep these lectures short because this is difficult material. And so I'm going to end by going all the way back to Popper. It can be frustrating trying to evaluate the testability of quantum predictions, just like it can, Nate Silver at 538.com tries to predict elections. Sportscasters try to predict whether the Broncos are going to win or not. And if people make chancy predictions, if Nate Silver says there was a 90% chance that Biden would win the election, just as he said in 2016 that there was a 30% chance that Trump would win the election. Well, Trump won, Biden won. Are Silver's predictions tested and passed, or tested and failed, or untestable? It's very difficult to falsify probabilistic predictions, right? Because things that are unlikely are supposed to happen a certain amount of the time. And so if you evaluate quantum mechanics just one observation at a time, it can look really unimpressive. You can imagine your inner Karl Popper saying, yeah, you're just telling me there's a chance the particle will be detected here, and there's a chance it will be detected there. And you're right, it's detected in one of the places you said there was some chance of it being, but that's not very impressive. It can look more like astrology than a real science. That's a crucial misunderstanding of how quantum works, though. It makes very precise predictions once you repeat experiments over and over and over, right? It says that a certain result is random. And so the long-term frequency of it might, for instance, be 50%. Or it says there's going to be an almost 75% divergence in the results excuse me, of something like Bell's experimental setup. So if somebody makes probabilistic predictions and their results fit perfectly over and over and over, right? If 60% of the time that they say the Broncos are going to win, if they give the Broncos a 60% chance of winning, and in all such cases, they win 60% of those results. And if whenever they say the Broncos have an 80% chance of winning, over the long term, 80% of the time it happens. If every probabilistic prediction is vindicated with mathematical precision over and over and over, then that's a very rigorous kind of testing. And that's what's really going on in quantum theory, right? It can be pretty weak to say there's a chance something is going to happen. That underestimates quantum theory. It tells us what the chance is, and it makes very bold, very precise predictions. And you can repeat these experiments, and the predictions are the best that human beings have ever achieved. All right, that's part 2 of my discussion of DeWitt's chapter 28 on non-locality and quantum theory. One more part, and you are done with philosophy of physics. Hang in there, folks.